Hey guys, welcome to the fourth session of number systems on your e-learning platform Origins e-Shala. As I have been saying since last lectures that this playlist of quantitative aptitude is not just for CAT but all of the several aptitude exams where you may find that this topic makes your core foundation. So with that said, let's begin today's practice set. Here's the first question for today and of course the 13th question for this whole series. And obviously whenever I'm doing these questions, I hope you guys pause the video, try the question yourself and then start the video to see how I approach this and match what you did separately and which one is the better approach, because there are chances you may be already be knowing a better approach to this, which is possible that I may not know, and it would be more suited to you. The approaches that I show are generalized and suitable for everyone, which I think is the most best for generally for everyone. And with this, let's begin. And this time around we are having two positive integers, one is prime and one is composite. Okay, and I need to find which of this is statement true. So here the question preparer has played a very smart trick that you need to be aware of, that even though the question is about prime and composite, our options are not exactly about that. Our options are about whether it is an odd or even number. So that you need to be keeping in mind. So let's just get it out of the way, that what are our possibilities for both these numbers. X can be 2, 3, 5, 7, any prime number basically, and y can also be any composite number. That's our limitation and options. Now if I have to prove the first statement wrong, that their subtraction cannot be even, then I will try to prove that it is even, right? So intentionally I will take two similar, because I know for sure by basic addition subtraction that odd plus odd and even plus even, and of course the subtraction as well, result in even final answer. So that's why I have to select the same combination. Like if x is 2, then y will also be 6 or any even number for that matter. But if I am taking x as 3, I will ensure that y is another odd number. Okay, that's how you need to approach it. So here simply I will just do the operation and prove that I am getting an even integer. So I will directly eliminate the first option. As for the second, it is a multiplication. In multiplication, at least one of them, if I prove it is even, then my thing is done. So I will take x as the even one and y as the odd one. Of course, it can be opposite as well. You can keep x as any odd prime number and y can be even composite number. So at the end of the operation, you will get that yes, you are getting final answer as the even. So second option can also be eliminated. Similarly, for the third case, this time around you cannot directly cannot interpret directly whether this is going to be odd plus even or final answer would be whatever, but you can at least try to imagine that you have to prove it to be even. So I will again think of both numbers to be of same type, like 3 and 9 both are odd, so their summation will give me even number, and I will divide it by a odd number. So I'm getting even number, because if for a odd numbers multiplication, the only way it can be even is because a even number was multiplied to it. If I am saying I am getting an even number by multiplying something to an odd number, then obviously the number which was multiplied was even. That's why the final answer was even. That was the logic I used here. I made the numerator even. So no matter what the denominator is, my final value will definitely be even. Okay. So with that said, our final answer will be none of the above, because all of these statements we have proven them to be false. Moving on to the next question. This time around, I think many of you who have been watching this series since the first lecture will find it at the blink of in just a blink. You don't even need the options for this, I think, right? So I need to find 4 such prime numbers in ascending order such that the first 3, their multiplication will give me 385 and the last 3 will give 1001. Now, if you remember the game time from the last sessions, I'm sure you already know the answer. It is going to be 1001 equal to 7 into 11 is 13, and 385 will be by 5 into 7 into 11. This is because you have seen the past lectures, but how would I logically approach this if I didn't knew this? Just in case. So if I am talking about 4 such prime numbers in ascending order, I will just try to stick with the basic primes first. So my options will start from 2, 3, 5 and 7 on so on, right? But here I can clearly see the products that I am to get are odd. 385 and 1001. Both of them are odd. So that clearly means that in this operation 2 was not included, because out of all the primes 2 is the only even prime. That is the if 2 was involved, then the final answer has to be even. At least 385 will have to be even, but it is odd. So that means it is clear that 2 is not part of the operation. Then I will try with 3, 5 and 7, which will definitely not give me 385. So I will move on to next. And that in that case, I will directly come to 5, 7 and 11, which will give me my final answer 385, and 7, 11, 13, that will give me 1001. Now many will think about using XYZ and ABCD variables, but mind well, CAT is not about how much you know the process, but what kind of logic you interpret. Because here I clearly knew that 2 was not there, so I skipped it and started with 3. 357 I directly tried and I got that 385 is not there. Even if you put your logic here, just add 3, 8 and 5. What will you get? 16, right? And 16 is clearly not a multiple of 3. So I will not even bother using 3. I will directly start with 5 because I can clearly see 5 was used here. In 385, 5 is clearly at units place. That means 5 was used. Okay, that's the logic I came up with when I saw this question, even without knowing this our game time multiples. Okay, so let's move on to the next question. I'm sure this jogged up your memory and why that pair of 3, 5, 7, 5, 7, 11 and 7, 11, 13 is important. And of course our answer for this, the first number in the series is 5, so that will be our answer. Now this time let's do a bit of wordplay. I'm having prime numbers in the form of a plus 2, a plus 4, and I need to find the number of possible solutions of a. That means what prime numbers can I put at a such that a plus 2 and a plus 4 has to be prime as well. That is what this question is saying. So I need to find the number of solutions, not the exact value, but the number of solutions. Mind well. So I need to think like a plus 2, a plus 4, and if I can see, this is an arithmetic progression that we are adding 2 after each number. So, and I know one thing for sure, this is only possible after 3, because 2 and 3 there is difference of 1. That means they are clearly not part of this sequence. But 3, 5, yeah, there is addition of 2. So let's try with first 3 primes out, neglecting 2 or excluding 2. That will be 3, 5, 7, and you can see that they are clearly following this pattern. So after this, now think logically, after this every prime you won't be getting 3 consecutive numbers in such a fashion. There will obviously be at least one of them which will have addition of more than 2. The reason being, till this point, till 3, 5 and 7, only the multiples of 2 were being skipped, which was the reason we were getting a consecutive addition of 2. But from this point onwards, the multiples of 3 and 5 as well will be gone. So after 7 you cannot take 9, after 9 and 10 will also be gone, and so on. Oh, let me just get this call.
Hello sir, Boromont here. Sir, I agree with you that multiples of 2 and 5 will no longer be in the sequence of prime numbers. But isn't it possible to get prime numbers with 7, 9 and 1 at units place consecutively? Still, we cannot be sure about that, right?
Maybe I should say it came at just the right time. I think many of you might be having that query. As he said, that there is a possibility that there will be prime number with having unit digit 9, 1 and 3, or we can even try 7, 9 and 1. That is a possibility, right? But if you think logically, you can try any 3 random pairs of such numbers which you find. Don't think about prime, just take any random numbers which you are still not sure whether they are prime or not. And as they said, any prime number can only have these numbers at their final position now. Any prime number, they cannot be 2. Definitely they cannot be 2 because it will be even. And 5 and 0 can also not come because that will be multiple of 5. That we are sure. But 3, 7 and 9 we are not sure. So we have to at least keep one of them there. But now if you try any consecutive integers with 7, 9 and 1 at units place, because these are the only ones which are having consecutive difference of 2, you will find that always at least one of them will be multiple of 3. Always. That's a fact. And you can even mark it as a note that after this point, there will always be a multiple of 3 there. So yeah, coming back to our main question, the only possible pattern was 3, 5 and 7. So the only solution I'm getting for A is the answer 3. So our final value will be option A. Only one solution exists. And I'm sure you guys enjoy such queries and their clarification. In that case, a like to our video and sub to our channel would be fabulous. And let's move on to our next question. Again, a combination of prime and your basic divisibility rule check. So this time around, we are going to be talking about primes which are greater than 3. That means 5, 7, 11 and all, and the list goes on. We all know it will be infinity. Never the cat will never directly say that this is the set of number you have to do. They want to waste your time, obviously. So I need to do this operation where I'm squaring the number and adding 17 and again dividing by 12, and I have to find the remainder. What will be the remainder every time? So let's try a few numbers. I will try with 5, obviously it is the smallest. So here I am definitely getting 6. 25 plus 17 will be 42. 42 divided by 12, I am getting 6. Okay. And then for 7 as well, I got 66. Again 60 and difference of 6. So for let's do 13 this time. 13 also I am getting remainder 6. At this point, I'm pretty much sure that this pattern is going to repeat. You can even try others numbers, but I know already because I created this question just to remind you that there are several properties of prime and this is one of them. When you square a prime number and add 17 to it, divide it by 12, you will get this pattern. That remainder will always be 6. So our answer will be 6. You don't need to mug it up. Just remember that even though there are infinite possibilities, you can finalize your answer using the few limited options. No need to panic just by seeing so many combinations and possibilities. You can always try with small values. Okay, so let's try the last question for this session. Or maybe before that, let's brush up a few things. I think this is fourth session and I taught this to you in first session, so a better revision for you guys. This time, I got several comments of students saying or suggesting rather that whenever we get a decimal to be turned in fraction in this form, it is better to split them up like this. But if you try to solve it now, obviously you can find for 2, 3, 157, 157, 157, 3 numbers are repeating. So I will put 3 nines below and 2 numbers are not repeating. So I will put 2 zeros below and I will subtract the 2, 3, 157 with 23. But at the end, whenever I am getting this simplified value, I will again have to add it with 3 to get it to final fraction form, and that will involve multiplication, simplification and also. So your steps are increasing. You can clearly see your steps increased from about 3 steps were increased. But if you try to do it directly as we have been doing, so I will take the whole 32357 and subtract 323 rather than 23 and the operation will be same. But you will notice the final answer is still the same. So yeah, both are the approach will give you the same answer. It's just about what you are more comfortable with. And in any case, if your calculation is fast and you are comfortable with the first option, you can definitely go ahead with that. But I still prefer the second option because it saves my time. My calculation is not very fast. So here's the last question. This time around we have 5 integers and I am asked out of these 4, even though they are 5, I have to check for 4. So no need to waste time on S, which has to be compulsorily even so that this whole operation of p square into q cube minus r minus s plus t becomes even. Now, as we all know, for any number to be even, at least one of its factor will always be even. So I will try to split this whole operation in 2 multiples, that will be p and q cube r minus s plus t. Of course, many will say p square should come, but we are talking about factors. And p square is also factor and p is also factor. I wrote the bare minimum, smallest factor, which I could clearly identify just from seeing it at one glance. So, it doesn't matter whether p square as a whole is even or not. What matters is p is even or not, because that's what we are going to select, right? So here I can see if I try to make p even, it is quite possible that the final operation of q cube r minus s, this gives me odd. So odd plus even will leave me with odd again. That means whatever I am doing, the final simplest approach will be to make p even. Whenever p is even, it doesn't matter what the final operation is giving inside the bracket. Whatever it is, even by even into even or odd into even, final answer will have to be even. So it is clear that p has to be even, because once I multiply even number to any number, the final answer will always be even, as we see in the last few questions in this session only, if you have noticed. So that's why p is our final answer. So I hope you guys enjoyed the session. See you again in the next lecture. Thank you.